Hey, welcome back. Last time we were discussing reduced row echelon form and row echelon form. The reason we're interested in both of those forms, especially the reduced row echelon form, if you have it in reduced row echelon form, it's very easy to identify the solution to the corresponding system of linear equations. So that's the goal. What we want to do is learn a process now that will take an augmented matrix and get it into reduced row echelon form. One thing I want to point out, in row echelon form, leading ones have zeros below, and reduced row echelon form, leading ones have zeros above and below. So in fact, that's the only difference between row echelon form and reduced row echelon form. They will both have leading ones. In reduced row echelon form, you will see zeros both above and below each leading one. Now, before we go any further, we need these facts right here. So the first fact, every augmented matrix can be put in reduced row echelon form by applying elementary row operations. This is also true, also true for row echelon form. In fact, what the process we're going to learn, what it does is we'll apply row operations. We will first get row echelon form, then by applying some additional row operations, we'll get it into reduced row echelon form. Right? The second fact, reduced row echelon form is unique. So what that means, if two people are handed the same augmented matrix and told to put it into reduced row echelon form, they'll both go through this process. They'll both end up with exactly the same augmented matrix in reduced row echelon form. The same cannot be said for row echelon form. So row echelon form is not unique, but any two row echelon forms will have leading ones in the same spots. So that what I mean here, if two people are handed the same augmented matrix and said, put it in row echelon form, when the two people are done, the row echelon forms may not be the same, but they will have exactly the same number of leading ones, and they'll be in exactly the same spots. And these spots have names, so these are called pivot positions. And one more piece of terminology, the columns containing leading ones are called pivot columns. Okay, so now we have these facts in place. We can get going on the process of getting a matrix into reduced row echelon form. So that's our goal now. And the process has a name. It's called Gauss-Jordan elimination. So Gauss-Jordan elimination refers to the process of taking an augmented matrix and getting it into reduced row echelon form. There's also Gaussian elimination. Gaussian elimination is the process of taking an augmented matrix and getting into row echelon form. So Gaussian elimination stops a little bit short, and then by doing Gauss-Jordan, this additional step will get it into reduced row echelon form. We'll see how this goes now. So let's just start with an example. So the matrix I want to start with 0, 2, 4, 6 in the first row. 2, 4, 2, 0 in the second row. 4, minus 4, 0, 8 in the third row. So here's our augmented matrix. What I want to do is get this into reduced row echelon form. So first step. Identify the leftmost column with a non-zero entry. So it's possible, I mean, in this example, the first column has a non-zero entry. It's possible that you'll have an augmented matrix where the first column consists entirely of zeros, right? In which case, you just move on to the right till you find the first column, the leftmost column that has a non-zero entry. All right, so in our case, there it is. Now, so our next step, so I've got a non-zero entry in my first column. I would like a non-zero entry in the very top. In this case, I've got a 0 in the top. So remember, one of our elementary row operations, you can interchange any two rows. So what I'm going to do is interchange rows 1 and 2 so that I get a non-zero entry in the top. So this one may or may not be necessary. In our case, it is. So if necessary, interchange rows to get a non-zero entry in the top. So if I do that, in this case, what I'll have is 2, 4, 2, 0, 0, 2, 4, 6, 4, minus 4, 0, 8. Okay, so easy enough. All right, now what I'm going to do, I've got a non-zero entry right there. I'm going to turn that into a leading 1 by performing another elementary row operation. Remember, one of our operations is you can multiply any row by a non-zero constant. In this case, what I'm going to do is multiply this row by 1/2. So let me do that. This will be 1, 2, 1, 0, 0, 2, 4, 6, 4, minus 4, 0, 8. And let me write down what I just did. So create a leading 1 in the top row. Okay, now I've got this leading 1. I'm going to use that leading 1 to get zeros below it, right? By performing elementary row operation number 3. So let's say what that is. So add multiples of row 1 to the rows below to get zeros below the leading 1. Sorry, now I'm blocking that area there. So add multiples of row 1 to the rows below it to get zeros below that leading 1. So in this case, there's the only one that I need to deal with, is that 4 right there. So what I'm going to do, I'm going to multiply row 1 by -4 and then add it to row 3. So I'm multiplying row 1 by -4, so that gives me a 0 here. -4 times 2 is -8. Add it, I'll get a -12. -4 times 1 gives me a -4 plus 0, -4 there, and then that one will be 8. One thing I should point out, it is very easy to make an arithmetic mistake when you're doing this process, these row operations. Take it slowly. In fact, I'm having to reshoot this video because I screwed up. I made one little arithmetic mistake as I was going, and it screwed up the whole thing. So, there's no reason to rush. Take your time. Get it right the first time. Okay, now notice what we've done. We've got a leading 1 and zeros below it. Now what I'm going to do, I'm going to repeat this process on the submatrix that I'm circling or putting a box around right there. All right? We're done with the first row. Now let's move on. I want to turn that 2 into a leading 1 and then create zeros below it. So now we're going to repeat the process on the submatrix. It's the submatrix that you get by deleting row 1 and column 1. So on the submatrix, I'm just going to say indicated. Okay, so now I've got a little matrix right here. The first step, identify the column, the leftmost column that has a non-zero entry. There it is. Next step, if we had a 0 right there, I'd flip some rows so that I could get a non-zero entry right there. Next step, create a leading 1 right there. So what we'll have is 1, 2, 1, 0, 0, 1, 2, 3, 0, minus 12, minus 4, 8. Okay, now I want to create a 0 below my leading 1. How do I do that? Multiply row 2 by 12 and add it to row 3. Okay, so I multiplied by 12. When I add 12 to -12, I get 0. This will be 24 plus -4 gives me a positive 20 right there. 3 times 12 is 36, plus 8, 44. All right, now we've got a leading 1 with zeros below it. So now what I do, I repeat the process to the little submatrix that lies below the second row. Well, in this case now, all I need to do is create a leading 1 right there. And so 1, 2, 1, 0, 0, 1, 2, 3, 0, 0. So now I need to multiply by 1/20th. So that's going to give me a 1 here, and 44 over 20 is 11/5. Notice, if you look at this matrix, we're in row echelon form. Keep repeating this process until you get your matrix. If you have a giant matrix, you might have to do this a bunch of times, but by going column by column, creating leading 1s, moving over, creating leading 1s, eventually you'll get it into row echelon form. Okay, now what we want to do is get into reduced row echelon form. Now notice, we worked left to right before, right? Creating leading 1 in the leftmost column, moving over, moving over, moving over as we create leading 1s. Now what we're going to do is work right to left, and this leading 1, to get it into reduced row echelon form, I need zeros above each leading 1. I'm going to do that by working right to left. So I'm going to start with that leading 1. I'm going to use row operations to get zeros here and here. So step 5, working right to left, get or use elementary row operations to get zeros above each leading one. All right, so let's see. First, I would like to turn that 2 into a 0. 1, 2, 1, 0, 0, 1. So what am I doing? I'm going to add negative, or I'm going to multiply by -2. So -2 plus 2 is 0. This will be -22/5 plus 15/5. So that will be -7/5. Here we'll have 0, 0, 1, and 11/5. Okay, so now I want to use this leading one to turn that one into a 0. So that will be 1, 2, 0, -11/5, 0, 1, 0, -7/5, 0, 0, 1, and 11/5. I'm just going to check my work here to make sure I'm not making some mistake. Yep, looks good. Okay. One more step. Right? I've got zeros above this leading one. Now I need to have zeros above this leading one, so I need to kill off that 2 right there. Okay, so I need to multiply the middle row, row 2, by -2. Add that to row 1. 1, 0, 0, and let's see, if I go -2, that will mean that will be a 14/5. Add it to this one will give me 3/5. 0, 1, 0, -7/5, 0, 0, 1, 11/5. And there it is. Reduced row echelon form. So what we did Gaussian elimination to get it into row echelon form, and then Gauss-Jordan elimination is the process of going from our original augmented matrix to reduced row echelon form. Okay, we just did an example taking an augmented matrix, getting it into reduced row echelon form using this process called Gauss-Jordan elimination. What's the point? Right? Why are we learning this? Well, the point is right here. I've already written it down. If the augmented matrix of a linear system is in reduced row echelon form, the solution is easy to find. So our process is going to be, if we're handed a linear system, and linear systems are going to come up in this class the entire time, right? For the entire quarter, we'll be seeing linear systems arising for one reason or another. So if you start off with a linear system, replace it with the corresponding augmented matrix, get that augmented matrix into reduced row echelon form, you will then be able to identify the solution set to that linear system. That's the point. Okay, so now there's a little bit of terminology that goes along with this. So remember, when you have an augmented matrix, each column corresponds to a particular variable. Right? So variables corresponding to pivot columns are called leading variables. Now, so there's some variables that are going to correspond to pivot columns. The others, the remaining variables, are free variables. So we've got leading variables and we've got free variables, right? Either corresponding to pivot or non-pivot columns. All right, so now I want to do some examples, and the instructions will be the same all the way. So let's solve the systems. In the variables x1, x2, x3, and x4. Let's say it like this. All the systems. Okay, so first example. 1, 0, 0, 0, 3. 0, 1, 0, 0, negative 1. 0, 0, 1. 0, 4. And 0, 0, 0, 1, 0. Well, what is this telling us? If you think about what this augmented matrix would say, if you reverted back to the corresponding linear system, it would tell us x1 is equal to 3. It would tell us x2 is equal to negative 1. It would tell us x3 is equal to 4. And it would tell us that x4 is equal to 0. So in this case, we've got a system. It has 4 variables, right? And then this last column that corresponds to the stuff that's to the right of the equal sign. Right? And so if we had a system, we got it in, and we converted to the augmented matrix, and then got into reduced row echelon form that looked like this, then the system would have exactly one solution. And if we wrote it in ordered tuple notation, it would be 3, 1, 4, 0. Okay, so there's the first example. And notice in this case, and I should have written this down, this was the case where there was no free variables, right? So in that case, we ended up with a unique solution, exactly one solution. Okay, so now I'm going to write down another matrix. It'll be an augmented matrix corresponding to some system, and this augmented matrix will be in reduced row echelon form. So this one, once again, it's going to have 4 rows and 5 columns. So first one will be 1, 2, 0, 0, 3. 1, 2, 0, 0, 3. 0, 0, 1. 0, 0, 1, 0, 2. 0, 0, 0, 1. And 1. And then 0, 0, 0, 0, 0. So notice in this case, the pivot columns are column 1, column 3, column 4. Which means, right, so this one, and that one, those are the pivot columns, which means that we have one free variable. x2 is free. So what we're going to do to describe this solution here is we're going to write x2 equal to t. I'm going to give it, this is called a parametric form of the solution. Right? So I'm going to equate it with a parameter. Okay, so now what do we see here? We see that x4 has to equal 1. We see that x3 has to equal 2. And then we see that x1 has to equal 3 minus 2 times x2, 2t. So now let me rewrite my solution. My solution will look like this. x1 equals 3 minus 2t. x2 equals t. x3 equals 2. And x4 equals 1. So now, how do we interpret this? Every time we choose a new real number t and substitute it, that gives us a new solution. And by letting t run through all possible real numbers, that gives us all possible solutions to the original linear system. All right, so this is called the parametric form of the solution. And notice now, since we get a new solution for every choice of t, there are infinitely many solutions. All right, so I want to do some more examples. Same idea. I'm going to write down an augmented matrix in reduced row echelon form, and it corresponds to some linear system. We want to identify the free variables and the leading variables. The free variables are going to correspond to certain parameters. Right? I'm going to call them, well, we'll see as I go on this one. So, all right, next one. 1, 0, 3. 1, sorry. 0, 1, 0, 3, 1. 0, 0, 1, minus 1, 2. And then 2 rows of zeros. All right, so remember, we start off with some linear system, we do some elementary row operations, we eventually get it into reduced row echelon form, and it ends up looking like this. The columns corresponding to leading ones, right, the pivot columns, those are our leading variables. The other columns, which would be column 1 and column 4, those are our free variables. So free variable here, free variable here. So what do I do now? That tells me that x1 and x4 are free variables. So what I'm going to do is I'm going to write, let's say x1 equal to s and x4 equal to t. Right? And now I'd like to describe my solutions using these two parameters right here. So let's see, x3, right, looking at this equation right here, or this row right here, it tells us that 1 times x3 minus x4 is equal to 2. So I can say x3 is equal to 2 plus x4, which we wrote as t. So x3 equals 2 plus t. X2, that's equal to, so this equation, or this row, would correspond to the equation x2 plus 3 times x4 equals 1. So x2 is equal to 1 minus 3, x4, sorry. So that would be a t. Fix that. Like that. So what does our solution set look like then? x1 equals s, x2 equals 1 minus 3t, x3 equals 2 plus t, and x4 equals t. So what that means is every time we choose a new s and a new t, that gives us another solution to our system. Once again, we've got infinitely many solutions. All right, let's try one more example. Okay, so let's say now our augmented matrix looks like this. The first row, all ones. 1, 1, 1, 1, 1. Next row, 0, 1, 1, 1, 0. 0, 0, 1, 1, 0. And then the last row, 4 zeros followed by a 1. All right, now think about what this tells us. All right? Remember that this matrix corresponds to a linear system. What would that bottom row say? It would say 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 equals 1. That's impossible. What does that mean? There are no solutions. This is an inconsistent system. And in fact, that's going to be true in general. If you have an augmented matrix that has all zeros except a 1 in the last entry, right, that's going to tell us that there are no solutions. It's impossible, so we have an inconsistent system. Okay, so there's some examples. Now, we defined this, I think, in the first lecture, what it means for a system to be homogeneous. The corresponding matrix to a homogeneous system is going to be one that has all zeros in the right-hand column. So a linear system is homogeneous if the last column, the rightmost column, or the last column of the corresponding augmented matrix, let's say its augmented matrix, its has only zeros. So this is really just redefining. It's the same definition that we had before, except we're now phrasing in terms of augmented matrices rather than linear systems. Now, one thing to be aware of, so let's say note, homogeneous systems are consistent. Why is that? Well, think about it this way. Or let's just identify who the solution would be. If we choose x1 equal to 0, x2 equal to 0, x3 equal to 0, all the xi's equal to 0, right? That gives us a solution, right? So the reason x1 equal to 0, x2 equal to 0, dot, 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 xn equal to 0 is a solution. And remember, we said that we defined a solution or a system to be consistent if there's at least one solution. Here's another fact, I guess we could say. A homogeneous system with more columns. Oh, how do I want to say this? I should say more variables, not columns. More variables than columns has infinitely many solutions. Has infinitely many solutions. Now, what's the reason? Well, if you've got more variables than you have columns, then there will be at least one free variable. Thinking about the process that we went to, went through, each time we have a free variable, what do? We correspond that with a parameter, which means that we will get a solution for every new choice of real number that we substitute for that parameter. That gives us an infinite number of solutions. This is false in general, right? If the system is not homogeneous, right? This could not be, it's possible that this is not true. Okay, that's a good place to stop. So we will see you next time.